In order to guarantee full understanding of this course, you should have completed previous universal molding modules: MU1 Introduction, MU2 Fundamentals, MU3 Molding with Graphs, MU4 Material Morphology, MU5 Press Calculations, and MU6 Injection Unit Calculations. Your objective is to identify the needs of your process and to determine well-thought-out solutions. Because of this, before molding or making any type of adjustments to your injection molding machine, you should make certain initial calculations. These initial adjustments are known as molding from the desk. Remember that you are dealing with expensive equipment and should not rush your work. In this lesson, we will discuss material consumption, heat removed, Q, water flow, estimated cooling time, temperature control units, material consumption. To determine material consumption for a particular mold, you should know approximate process cycle time in seconds, quantity of material required for the mold, in grams or in the units that you prefer.
How do I know the cycle time and the amount of material consumption if I don't yet know the process?
Good observation. That data can be provided by the product designer or the mold maker. Material consumption equals amount of material divided by cycle time. Example: for a mold for polycarbonate components, the total weight required to fill the mold is 275 grams, and the expected mold cycle is 9 seconds. Material consumption will equal 275 grams divided by 9 seconds. That will equal 30.6 grams per second. This means that the process will consume around 31 grams per second, or 246 pounds per hour, or 112 kilograms per hour. Heat removed, Q. Heat removed, Q, is the amount of heat removed by mass unit in a particular thermoplastic. This is normally measured in units of BTUs per hour, kilowatts, and cooling tons, where 1 kilowatt is equal to 3,415 BTUs per hour. 1 cooling ton for a chiller is equal to 12,000 BTUs per hour. A cooling ton for a tower is equal to 15,000 BTUs per hour. Heat removed Q equals the amount of total material times the energy required for that material, all divided by process cycle time, where the amount of total material equals the amount of material it takes to fill the mold in grams. Energy required for the material equals the heat energy removed from the material per mass in joules per gram, and the process cycle time equals the duration of the cycle in seconds. The following table demonstrates the energy required for certain materials. Here we find that polycarbonate, PC, will require 368 joules of energy for each gram, or 158 BTUs for each pound. Remember that the values in this table are provided only as a reference. Obtain the real values from your resin supplier. Example: a mold is used to make polycarbonate components, with a total weight of 275 grams needed to fill the mold and an expected cycle of 9 seconds. How much heat will be consumed? The previous table lists polycarbonate as requiring 368 joules per gram of energy. Substituting into the heat removed equation, we have 275 grams times 368 joules per gram, all divided by 9 seconds. This equals 11,244 joules per second. This can be converted into 11,244 watts, or 11.24 kilowatts. This means that, to cool this mold, it would consume 11.24 kilowatts, or 38,400 BTU per hour from the cooling system.
How can this be used when specifying the load to a chiller or to a cooling tower in tons?
Easy. By using the previously given conversions. A cooling ton for a chiller is equal to 12,000 BTUs per hour, and a cooling ton for a tower is equal to 15,000 BTUs per hour. For a chiller, 38,400 BTUs per hour times chiller tons divided by 12,000 BTUs per hour equals 3.2 tons. For a cooling tower, 38,400 BTUs per hour times cooling tower tons divided by 15,000 BTUs per hour equals 2.6 tons. This means that the mold connected to a chiller would need a load of 3.2 tons, and if connected to a cooling tower would need a load of 2.6 tons. Another method utilized by the industry is charts provided by the cooling equipment manufacturers. For example, in the table to the right, we can see that, when using a chiller, Polycarbonate has a requirement of 1 ton of refrigeration for 30 kilograms per hour, or 65 pounds per hour, of material. In a previous example, we had a mold for polycarbonate components with a total weight of 275 grams and an expected cycle of 9 seconds. According to the table, the energy factor for PC is 30 kilograms per hour per ton, or 65 pounds per hour per ton. Material consumption is equal to total amount of material divided by process cycle time. In this case, it equals 110 kilograms per hour, or 242 pounds per hour. Heat removed Q equals material consumption divided by thermal load of the material. This means 110 kilograms per hour divided by 30 kilograms per hour per ton, or 242 pounds per hour divided by 65 pounds per hour per ton, will equal 3.7 cooling tons. So according to these calculations, the chiller equipment will see a load of 3.7 tons.
Why is the load obtained in this example different from the load calculated in the previous example?
Important question. In each example, the constants used for polycarbonate come from different sources. That is why you must make sure that your constants come from reliable sources, such as your resin manufacturer. Water flow. Water flowing through the mold removes heat from the melted material that is inside the mold. Consequently, the water's temperature will rise, an increase known as delta T. Delta T is equal to outlet water temperature minus inlet water temperature. The mold's cooling water hose connections should be parallel and not in series. A connection in series does not guarantee equal heat removal throughout all the cavities in the mold. In other words, the cavities where the flow begins will have a heat removal that is distinct from the cavities where the water exits. Even though it's easier to create a connection in series, the connection should be parallel. This will guarantee uniform heat removal and uniform temperature distribution in the cavities.
How uniform should the temperature be between the cavities?
There should be less than 2 degrees centigrade or 4 degrees Fahrenheit difference between cavities. Consult the mold designer on the optimal cavity temperature differential for your mold.
What temperature are we speaking of? The temperature of the water or that of the metal surface of the cavities?
The metal surface of the cavities. Though the water removes the heat, the temperature of the metal is the most significant. Another effect about which you should know is that the water flow around the mold should be turbulent and not a laminar flow. Turbulent flow is more efficient in removing heat.
How do I know if the water flow is turbulent?
Turbulence is achieved by increasing the water flow that enters the mold. This flow should be sufficient enough to guarantee a factor, called Reynolds number, that indicates whether the flow is turbulent or laminar. This factor is a function of the flow and the geometry of the cooling channels. A simple way of guaranteeing turbulence is reducing the delta T of the water moving through the mold. For example, with rapid processes, less than 10 seconds, delta T should be around 1 degree centigrade or 2 degrees Fahrenheit. With slow processes, longer than 30 seconds, delta T should be around 3 degrees centigrade or 5 degrees Fahrenheit. With average processes, delta T should be around 2 degrees centigrade or 4 degrees Fahrenheit. Consult your mold designer as to which water flow, water temperature, and delta T are best for your mold. Water flow is determined with the following equation. Water flow Q is equal to little q divided by Cp times delta T, where Q is equal to water flow, little q is equal to heat removed from the plastic per cycle, Cp is equal to the specific heat of the water, and delta T is equal to outlet water temperature minus inlet water temperature.
Is the specific heat, Cp, always related to water?
Not necessarily. Extremely hot processes use oil, and very cold processes use a mixture of water and antifreeze. Obtain the value of Cp that corresponds to the heat transfer fluid that is being utilized. The specific heat of water at 13 degrees centigrade or 55 degrees Fahrenheit is equal to 4.196 kilojoules per kilogram centigrade or 1 BTU per pound Fahrenheit. Example: a process consumes 190 grams of polypropylene every 12 seconds. The inlet water temperature is 13 degrees centigrade or 55 degrees Fahrenheit, and given that it is an average cycle, we can assume a delta T of 2 degrees centigrade or 4 degrees Fahrenheit. What will be the required heat consumption and water flow? The constants are the following. Energy required of polypropylene is 670 joules per gram. The specific heat Cp of water at 13 degrees centigrade or 55 degrees Fahrenheit is equal to 4.196 kilojoules per kilogram centigrade. The density of water is 1 kilogram per liter. Substituting into the equation for heat removed, we have 190 grams times 670 joules per gram, all divided by 12 seconds. This equals 10,608 joules per second, or 10.61 kilojoules per second. Substituting into the water flow equation, we have 1.264 kilograms per second. This can be converted into 1.264 liters per second, which is also 75.85 liters per minute, or 20.1 gallons per minute. This process will require a water flow of 75.9 liters per minute, or 20.1 gallons per minute. A simpler way to determine the required water flow of a chiller for a process is with the following equation. Gallons per minute equals 24 times chiller tons, all divided by delta T. To determine the water flow of a cooling tower for a process, gallons per minute equals 30 times cooling tower tons, all divided by delta T, where GPM equals gallons of water per minute. Chiller tons equals the chiller tons required to cool the mold. Cooling tower tons equals the cooling tower tons required to cool the mold. And delta T equals outlet water temperature minus inlet water temperature in Fahrenheit. Delta T in Fahrenheit is equal to 9/5 of delta T in centigrade. With fast processes, less than 6 seconds, delta T equals 2 degrees Fahrenheit, about 1 degree centigrade. With slow processes, longer than 30 seconds, delta T equals 5 degrees Fahrenheit, or around 3 degrees centigrade. With average processes, delta T equals 4 degrees Fahrenheit, or around 2 degrees centigrade. In the previous example, the process consumed 190 grams of polypropylene every 12 seconds, with a delta T of 2 degrees centigrade, or 4 degrees Fahrenheit. What will be the required heat consumption and water flow? Using the equation for material consumption, where material consumption equals the total quantity of material divided by the process cycle, we have 190 grams divided by 12 seconds, which equals 15.8 grams per second. This can be converted into 125 pounds per hour. According to the thermal load for refrigeration table shown previously, we find that polypropylene needs 35 pounds per hour per ton. To obtain the load in tons, we use the heat required equation. Substituting, we find that heat required equals 125 pounds per hour divided by 35 pounds per hour per ton. This is equal to 3.6 chiller tons. The required water flow of a chiller for the process is obtained with the equation gallons per minute equals 24 times chiller tons, all divided by delta T. Substituting, we find that this equals 21.5 gallons per minute. According to this method, the chiller will see a load of 21.5 gallons per minute at a delta T of 4 degrees Fahrenheit. Once again, the result obtained is distinct from the results of the previous method, since this equation is an empirical approximation and the constants come from different sources. Estimated cooling time. Cooling time is a universal control parameter that can affect the dimensional result of the molded parts and can also affect the recovery stage. Cooling time, by itself or combined with the temperature of the mold, can affect the thermal dimensions of the product. Determining the cooling time is important and should be done before starting a process optimization laboratory. Cooling time is initially adjusted with an excessive value and is then optimized with a molding laboratory. This is adjusted more than is required in order to avoid affecting the other parameters that were previously determined.
How can I arrive at this extended cooling time value?
There is a simple way and a calculated one. The simple way is asking the mold manufacturer or someone that you trust that has molded with a similar mold. Take the recommended cooling time and add to it 30%. Extended cooling time equals recommended cooling time times 1.3. The calculated method is determined by using the following equation. The result of this equation could have up to a 30% error. Even so, for our purposes, it is a good tool. Tx equals heat deflection temperature. Tm equals mold temperature. Tp equals plastic melt temperature. T equals part thickness. Alpha equals thermal diffusivity. Note: use the table to find the values of the constants for the material that most resembles yours. Temperature control units. The temperature control unit, or TCU, is responsible for maintaining a constant flow and temperature. While molding, the removal of heat from the mold is what determines the thermal dimensions. Remember, these dimensions are a function of shrinkage. Water flow, as well as water temperature, is a factor that we must control during the removal of heat. Other parameters that we must understand are pressure loss and temperature loss. The water pressure drop in the mold, delta P, equals inlet water pressure minus outlet water pressure. The loss of water temperature in the mold, delta T, equals outlet water temperature minus inlet water temperature. During the process, delta T and delta P must not change. Any change in these could cause a variation in the thermal dimensions of the molded parts. Variation in delta T could be a consequence of dirty channels, changes in the process, changes in water flow, or change in melt temperature. Variation in delta P could be a consequence of dirty channels, channels blocked by an object, incorrect connection, or tubing of a smaller diameter. The source of cooling could be either a chiller or a cooling tower. Using a pump and a valve, we maintain a constant temperature and water flow. TCU with direct cooling. The principal components are pump, in charge of guaranteeing the water flow throughout the mold. Cold water intake, allows cold water from the chiller or cooling tower to enter the TCU. Cooling valve, this discharges hot water from the TCU to the chiller or the cooling tower. Thermocouple, measures the water temperature entering the mold. Control, this is the brain of the TCU and controls parameters such as the temperature of the water going to the mold. The operation of a temperature control is simple. A constant water flow and water temperature are maintained by means of a pump and a valve. Let's look at its operation in more detail. The pump is in charge of guaranteeing the water flow between the TCU and the mold. When the control detects that the water's temperature to the mold is increasing, it opens the valve so this hot water can return to the chiller or the tower. Then cool water enters the TCU from the suction side of the pump. TCU with direct cooling and direct heating. By using a pump, a valve, and a heater, a constant water flow and temperature can be maintained. The cooling source is a chiller or cooling tower. It includes the heater to help efficiently increase the temperature. The principal components are pump, in charge of guaranteeing the water flow throughout the mold. Cold water intake, allows cold water from the chiller or cooling tower to enter the TCU. Cooling valve, this discharges hot water from the TCU to the chiller or the cooling tower. Thermocouple, measures the water temperature entering the mold. Heater, activates to help efficiently increase the water temperature. Discharge valve, is a security device that protects the system from overpressurizing. Control, this is the brain of the TCU and controls parameters such as the temperature of the water going to the mold. Let's look at its operation in more detail. The pump is in charge of guaranteeing the water flow between the TCU and the mold. When the control detects that the water's temperature to the mold is increasing, it opens the valve so this hot water can return to the chiller or the tower. Then cool water enters the TCU from the suction side of the pump. The heater only activates to increase the water temperature when the process needs it.
Why use a heater if we could use the heat of the mold and the system's friction to heat the water?
From the point of view of energy cost, adding a heater would seem to be inefficient, but that's not necessarily so. The heater only activates when needed. We can safely assume that, during the startup of a mold where the chiller water reaches 30 degrees centigrade and we want to operate at 90 degrees centigrade, it would take too much time to reach our operating temperature if we depended upon friction and the heat of the mold. Also, during the optimization of thermal dimensions, where various water temperatures must be evaluated to study their effects, we would have to wait too much time between each temperature increment.
What happens if the TCU pump doesn't guarantee the determined flow for a particular mold?
Among other things, there could be a variation in thermal dimensions between cavities, and the cooling time could be extended.
Are there molds that must be connected to more than one TCU?
Yes, they exist. It is very common to see more than one per mold. This makes it easier to demold the parts, correct bending, and guarantee some mechanical characteristic of the molded part, such as stopping crystal formation in a specific location of the molded product, etc. There are other TCU styles, such as negative flow, closed circuit, and with oil. Negative flow. Using suction, it creates negative water pressure in the mold, resolving filtration problems. Closed circuit. This separates the mold water from the process water in order to minimize deposit of contaminants and minerals in the mold. With oil. The transfer fluid is oil, which permits high temperature ranges, from 120 degrees centigrade to 290 degrees centigrade, or about 250 degrees Fahrenheit to 550 degrees Fahrenheit. Each TCU provider offers multiple options. One option to consider is mold purging. This device permits the mold water to be flushed, avoiding water spillage during mold maintenance. All of this equipment comes with protection devices. Some of these are adjustable alarms, and some are pre-adjusted in the factory. Some adjustable alarms are temperature limits and pressure limits. Some alarms that are adjusted at the manufacturer are for the system's maximum operational temperature and for the minimum pressure allowed to come from the chiller or cooling tower. These alarms mainly protect the equipment.
Why are there alarms that guarantee a minimum pressure from the chiller or tower?
The minimum pressure alarm protects the water pump from being damaged by cavitation. The water coming from the chiller pressurizes the water entering the TCU and is typically more than 1 bar in order to not damage the pump.
How do I know whether to connect the TCU to a chiller or to a tower?
Very good and significant question. First, you should know that the temperature of the chiller or tower should be at least 5 degrees centigrade or 10 degrees Fahrenheit colder than the required temperature adjustment of the TCU. This is done to compensate for the loss of heat due to friction and due to the heat that comes from the mold. If the cooling tower provides water at 30 degrees centigrade, connect it to TCUs that operate at 35 degrees centigrade or more. Every mold that requires less than 35 degrees centigrade should be connected to a chiller. A significant benefit to the TCUs is that the pump guarantees a constant flow between the TCU and the mold, no matter what is happening in the rest of the factory.
What do you mean, no matter what's happening in the rest of the factory?
Understand that if the TCU didn't exist and cooling occurred because of a direct connection to a centralized chiller or was being shared with other processes, the mold would be subject to anything that was happening with the shared water lines. Consider 3 machines with similar molds that share a chiller. Under an ideal operation, the water flow from the chiller is shared among 3 machines. But what would happen if one of the machines is stopped for mold maintenance? The water flow previously going to that machine from the chiller would now be shared between the 2 other molds. This could consequently affect the thermal dimensions of the molded parts. In the same manner, imagine that on a Monday, all the machines are started up after being shut down for the weekend. Each time a machine is started up, it will affect the machines already operating. An extremely complicated scenario. Summary. Part of the heat transmitted to the circulating water between the TCU and the mold comes from friction. Hoses should be connected in parallel. Water flow should be turbulent. The delta T for water should be less than 3 degrees centigrade or 5 degrees Fahrenheit. The surface metal temperature of the cavity should be uniform, with the differential of less than 2 degrees centigrade or 4 degrees Fahrenheit. Water delta P should be maintained throughout the mold. Water delta T should be maintained throughout the mold. A TCU isolates the water flow from a centralized system to the mold.
Let's review.